In this video, I will go over the questions in the final exam of Chemistry 473 in spring quarter 2021. I will skip question 1. Now question 2. Name this transition metal complex. We have 4 aqua ligands, 2 colloidal ligands. The oxidation number of cobalt is plus 3. Because you have plus 3 here, minus 1 together, it's plus 1. So how do we name this? This colloidal ligands are on the cis positions. So we need to say cis, tetra aqua dichlorido, cobalt 3. Now this complex bears overall -2 charges. Each cyanido is -1 charge, so this zinc is zinc 2. The name is tetracyanide zincate with an oxidation number of 2. Again, if the complex bears a negative charge, you need to add ATE at the end of the name of the metal, so it's zincate, ZINCATE. Question 4, the molecular formula of this. So overall, this is neutral because you have plus 2 on palladium, you have -1 on bromido, -1 on cyanido. Triphenylphosphine is neutral, so we're going to write this palladium, bromine. We put cyanido in a pair of parentheses. Not to be confused with 1 carbon atom and 1 nitrogen atom separately bonded to palladium. And then we have bis triphenylphosphate. 2 such ligands. And then we're done. The total charge again is 0. Plus 2 here, -1 on bromido, -1 on cyanido. Question 5. How many isomers are possible for this? Only 2. Cis versus trans. Which of the following ligands cannot be used to form a chelate complex? This ligand has only 1 point of attachment. That's this phosphorus. So this cannot be used to form a chelate complex. Question 7. There are 2 formation reactions. We just need to look at the statistical factor here. Over here, when L replaces water, there are 3 options, right? There are 3 aqua ligands, so 3 options. Over here, when water replaces L, there's only 1 option. So the statistical factor for this reaction is 3 divided by 1. Equals 3. Now over here, when L replaces water, there are 2 options. When water replaces L, there are also 2 options. So the factor is 2 over 2 equals 1. So again, for this reaction, the statistical factor is 3. For this reaction, the statistical factor is 1. And then we need to look at the ratio between these 2 statistical factors. So 1 over 3 is 0.33. Which of the following transition metal complexes are low spin? Cyanido, strong field ligand, so low spin. Re, 4D transition metal, low spin. Rhodium, 5D, low spin. Manganese, that's 3D, and water ligands are weak field ligands, so do not choose this one. This is high spin. The LFSE is pretty small, and therefore the D electrons prefer to be separated as much as possible. So this results in a high spin electronic state. Question 9, 0. Overall, we have 4 minus charges. Each cyanido is -1. Therefore, iron is +2, iron plus 2 has 6 d electrons. And then this cyanido is strong field ligand, so this 6 d electrons occupy the bottom 3 T2G orbitals. All 3 orbitals doubly occupied. Therefore, we have 0 unpaired electrons. Question 10, we're looking for the largest LFSE. The transition metal is iron, so we choose iron 3 rather than iron 2 because iron 3 has more positive charge. They're bonded to the ligands more strongly. And then you have amine ligands versus carbonyl ligands. Carbonyl ligands are strong field ligands. Amine is in the middle. Which of the following electron configurations results in a stronger Young-Taylor effect? This is a little tricky. D3 has 0 Young-Taylor effect. D10 has 0 Young-Taylor effect. D8 also has 0 Young-Taylor effect. When you have D8, 6 d electrons occupy the bottom 3 orbitals, and then you have 2 electrons, each occupy one of the 2 top orbitals. So only D4 has some Young-Taylor effect. If it's low spin, weak Young-Taylor effect. If it's high spin, strong Young-Taylor effect. So anyway, D4 more or less has some Young-Taylor effect. The other 3 has 0 Young-Taylor effect, so we choose D4. This is pretty simple. This superscript 6 is equal to 2s plus 1, so s is 2.5. And this symbol means L is 0. All right, SPDF correspond to L being 0, 1, 2, 3. SPDF 0, 1, 2, 3, so over here it's 0. Question 13, pale or colorless transition metal complex. Usually you need to think of spin forbidden transitions. All right, pale or colorless, that means the intensity of the electronic transition is extremely low, that's spin forbidden. And when you have high spin D5, only one electronic state has a spin multiplicity of 6. That's the ground electronic state. Therefore, all electronic transitions from the ground electronic state is spin forbidden. So this question 13, is related to question 12. Over here, it's actually 6s. The ground electronic state has this 6s atomic term over here. High spin D5 is 6s atomic term in its ground electronic state. All right. All other excited electronic states have a spin multiplicity lower than 6. All right. So again, if the ground electronic state of this high spin D5 is 6s over here, and none of the excited states has this spin multiplicity 6, that means all possible electronic transitions from the ground electronic state are spin forbidden, and therefore it's going to be pale or colorless. Question 14, very intense color. You need to think of charge transfer. So when you have D0, that means the electronic transition must involve electron transfer from the ligands to the transition metal. One example is permanganate with a very intense purple color. Permanganate KMnO4. This manganese has +7 oxidation number, that means 0 d electrons, and it has a very intense color. Because electronic transition in this permanganate involves electron transfer from the ligands, oxidal ligands, to the manganese transition metal center. The DD transitions are symmetry forbidden in tris tricyclohexyl phosphine platinum because the d orbitals all have the same G symmetry. This is false because if you look at this complex, it belongs to the D3H point group. There's no inversion center in this point group. So the d orbitals on the platinum center are distorted. They no longer have the G or U symmetry. Neither G or U. The formation constant of this reaction mechanism differs significantly when different L is used in the reaction. So over here, in the first step, it does not really involve L. In the second step, L enters the complex, all right, over here. And when different L is used, you have different formation constants. That means this step is really important. L entering into this is important, and this is associative. So, all right, so over here, M is bonded to 5 ligands. Here, M is bonded to 6 ligands. This is associatively activated. The second step is the rate limiting step. That involves this L entering this complex, so it's associatively activated. Which of the following ions is more labile? We'll choose the 3D transition metal with the lowest oxidation number, so it's iron 2. Question 18, the volume of activation is positive. That means in the rate limiting step, the reaction involves a dissociation step, so dissociative. All right, because dissociative reactions involve the increase of the volume when one or more ligands leave the complex. The volume increases. In a redox reaction, this structure is formed, obviously it's inner sphere mechanism. In the inner sphere mechanism, a ligand is bonded to 2 different transition metals. This serves as a bridge. This is a thiocyanidal ligand with 2 points of attachment. So this sulfur is bonded to one metal, this nitrogen is bonded to another metal, and the electron flows across this SCM bridge. Question 20. Highest rate of ligand substitution. We'll look for this 3D, transition metal cobalt 3D. Rhodium 4D, iridium 5D, 4D and 5D transition metal complexes are non-labile. Count the number of valence electrons in this. Well, I'm going to assume this palladium has an oxidation number of 2 because you have methyl with -1, fluorine with -1, amine is neutral, and all the complex is neutral, so you have +2 on palladium, -1 on CH3, -1 on fluorine. All right. And this is going to be for the 8 electron configuration. 8 d electrons plus 2 electrons from this methyl, 2 electrons from this fluorido, and 4 electrons from this 2 amine ligands. 8 plus 2 plus 2 plus 4, that's 16. Count the number of valence electrons here. Over here, this is considered cyclopentadienyl anion with -1 charge. Each C5H5 ring contains 6 pi electrons. All right, 6 pi electrons. And over here, this is also considered anionic with -1 charge. Therefore, this titanium has an oxidation number of +4. So +4 here, and each cyclopentadienyl bears -1 charge. Each SCH3 bears -1 charge. So overall, you have 0 valence electrons from this titanium 4 plus. 12 valence electrons from these 2 cyclopentadiene ligands, and 4 valence electrons come from 2 of these ligands. So it's going to be 0 plus 12 plus 4, that's 16. If you look at question 23, it's similar to question 22. The only difference is the ligand here is replaced with amine. And that makes a big difference here because amine ligands are considered neutral. So over here you have titanium 2+ with an oxidation number of 2. Alright, and then this is -1 charged, amine is neutral, so overall you have 2 d electrons from titanium and 12 electrons from these 2 cyclopentadiene anions and 4 electrons from the 2 amine ligands. 2 plus 12 plus 4, that's 18. So again, this is 16 over here, this is 18 because I changed this ligand with an oxidation number of -1 with this ligand with a 0 oxidation number. Question 24, smaller CO stretching frequency. This question tests your understanding of pi back bonding. So when you have carbonyl ligand bonded to a transition metal, usually it involves pi back bonding. The transition metal may donate the electrons back to the pi star antibonding orbital of CO. And the methyl groups are electron pushing groups, fluorines are electron withdrawing groups. So over here, the methyl groups help this transition metal donate the electrons to the pi star antibonding orbital of carbon monoxide. That will weaken the bond between carbon and oxygen. Therefore, you have a smaller stretching frequency. Question 25. Guess the value of N. We're going to assume the 18 electron rule. Let's say this cobalt is surrounded by 18 valence electrons. And this is a neutral complex, so I'm going to assume this cobalt is cobalt 1 with an oxidation of 1 because this is likely -1. Cyclopentadiene anion with -1 charge and 6 pi electrons here. Alright, cobalt plus 1 has 8 valence electrons. And this has 6 valence electrons, so 8 plus 6, that's 14. 14 electrons, and then 4 electrons from this carbonyl ligands. Right, so there are 2 carbonyl ligands, each contributing 2 valence electrons. So you may wonder, isn't this D8? You know, when you have a D8 complex, isn't 16 electrons common? No, that's 16 valence electrons are commonly found in 4D8 and 5D8 transition metal complexes because they have larger LFSE, and in that case the dx squared minus y squared orbital is usually empty. But in this case, cobalt is cobalt 1. This is cobalt plus 1 is 3D8. So still we're going to use 18 electron rule. Okay, 16 electron rule applies to 4D8 and 5D8 transition metal complexes. So when you have palladium 2+, platinum 2+, gold 1+, iridium 3+, rhodium 3+, and then those are 4D8, 5D8. And then you have a square planar structure with 16 valence electrons. Question 26, CH3 methyl group has 1 lobe with 1 unbounded electron. So chlorine has 1 lobe with 1 unbounded, occupied by 1 unbounded electron. So it's C. What about this one? This one has 3 unbounded electrons. All right, it can be 3 lobes, each occupied by 1 electron, or two lobes, one occupied by two valence electrons, the other occupied by one electron. But anyway, this is different. A and D are similar, so both are wrong. What about B, CH2? CH2 can be singlet or triplet. If it's a singlet, you have one lobe that contains two electrons, or it can be a triplet, you have two lobes, each occupied by one electron. Either way, it's different from CH3. All right? So A and D are actually isolobal as well. A and D are isolobal. C, chlorine, and CH3 are isolobal, so it's C. Question 27. This is pretty easy because titanium has only 4 valence electrons, so it can never lose 6 electrons anyway. And also, if you look at this catalytic cycle and count the number of valence electrons and calculate the oxidation number properly, it's going to be 4 for titanium in this catalytic cycle. In the Wilkinson catalytic cycle, the oxidation number of rhodium changes between 1 and 3. So over here, again, you need to be able to assign valence electrons properly. Usually you assign the electrons to the ligands. So when you have a hydrogen ligand, hydrido ligand, it's -1 charged. Halides are -1 charged. And methyl groups, ethyl groups, -1 charged. But if you have amine ligand, aqua ligand, carbonyl ligand, trimethyl phosphine ligand, those are neutral. What about ethylene? It's also a neutral ligand. All right, so over here we choose 1 or 3 after you carefully calculate the oxidation number of rhodium. It can be 1, it can be 3. So redox reactions are involved in this catalytic cycle. All right, I think I answered all questions.